Hello, today we're going to continue to look at section 2.3 in Algebra 2, and we're going to continue to talk about the factored form of a quadratic, but today we're going to focus on how we can use it and apply it in real-world situations. This first example we're going to do together. It says find the zeros of a quadratic function, but more importantly, it's a word problem. So it says Marco hits a golf ball into the air from the third level of a driving range that is 48 feet high. The function h of t equals negative 16t squared plus 32t plus 48 gives the height h in feet of the golf ball t seconds after it's hit into the air. Ultimately, they want us to figure out when will the golf ball hit the ground. Okay, so again, if we were to graph this on a graphing calculator, which we're not going to do, but you'd be hitting it from here and it would be landing over here. So we are trying to find this zero, but today we're going to learn how to do it by hand. In order to do that, it says right here, it's when the height is 0, which means I want to take this quadratic and set it equal to 0. And now we're going to solve the quadratic by using what we learned yesterday. Now the big difference with this one, we wrote it down as part of step 1, where we said, or part of step 2, I guess. Step 1 is to set it equal to 0, which it is. But in step 2, we said we are going to factor. But then I had you put in parentheses behind it, look for GCF first, greatest common factor. And I even said in the video, yesterday did not have any examples where you had to factor out the greatest common factor. But when you start to do these higher level problems with bigger numbers, you're going to want to check to make sure that it doesn't have, or that you can factor something out if you can. So in order for me to do that, I look at these three numbers. Since the 48 doesn't have a t, I know I can't factor out a t. But when I look at 16, 32, and 48, I actually know that they're all divisible by 16. Now the other thing we said when we were factoring, we said we wanted a to be positive. So as a result, I'm actually going to factor out a negative 16. Now one way to think about this, 16 times 1, 16 times 2, this is going to be 16 times 3. Okay, so just so you know that you can make these factor pairs. If they have something in common, that's what you factor out. But instead of just factoring out a 16, I'm going to factor out a negative 16, which means that I only have the t squared left from the first one. If I factor out a negative, though, that means that I have to change this positive to a negative. So it does switch your signs. I factored out the 16, which means I'm left with 2t. Don't forget to bring that t down. Really what you're doing is 32 divided by 16 is 1. That's how you can get there. Again, because I factored out a negative, this positive becomes negative. And again, if I take 16 or 48 divided by 16, I'm left with 3, and there's no t's. So I leave it like that. So when I'm factoring a quadratic, again, the first step is actually to look for the greatest common factor, which did not come up yesterday, but we'll see in some examples today. But now once I do that, then you're going to factor the inside the parentheses with what we learned yesterday. So factor the ax squared plus bx plus c. So I'm only going to worry about the t squared minus 2t minus 3, and the good news is that a of the t squared is actually 1. So I just have to focus on multiplying to get to negative 3 and adding to get to negative 2. The only two numbers that multiply to get to a negative, or to a 3, is 1 and 3. 1 has to be negative since it's a negative 3, and since I'm adding to get to a negative, the bigger number has to be negative. What that table helps me see again is that I can write t squared minus 2t minus 3 as the factors t plus 1 times t minus 3. All right, so step 1 again was to set it equal to 0. I didn't even write that down because it was already equal to 0. Step 2 is to factor. The new piece today is that sometimes you'll have to factor out that greatest common factor, and we just went through what that looks like. And then remember, the third step is to figure out what would make the equation 0. Technically, you're supposed to take all three factors in this case, because negative 16 is technically a factor, and you would set each one equal to 0, and then solve for t for your possible solutions. Problem is, when I set negative 16 equal to 0, there's no t in it, so I actually can't solve for anything. So if it's just a number as the greatest common factor, you don't actually have to worry about it. T plus 1, I would subtract 1, and I get t equals negative 1. Here I would add 3. I get t equals 3. Now remember, we want to know how many seconds it takes for the ball to hit the ground. Only one of these answers, though, makes sense. Okay? I got a negative. That was technically back here before the ball was hit. So while it is a solution, it doesn't make sense in the real world. However, it would make sense that this would be at 3 seconds. So 3 seconds is how long it takes for that ball to land. Okay, so we're building off of what we did yesterday, but it is a little more complex because we will have that greatest common factor, as well as this last step where you actually have to understand the solutions and which one or ones would make sense in the scenario. So I want you to go ahead and pause the video and try one of these on your own. A baseball is thrown from the upper deck of a stadium 128 feet above the ground. The function h of t is negative 16t squared plus 32t plus 128 gives the height of the ball t seconds after it is thrown. How long will it take the ball to reach the ground? So pause the video, set it up, remembering that reaching the ground is when h of t equals 0. So you're going to set that quadratic equal to 0, factor it, and solve. Here's the work I did. As I told you, I set it equal to 0. I once again could factor out that negative 16. So I was left with negative 16 times t squared minus 2t minus 8. I made my factor table and ended up with the pair of 2, negative 4, which means that it factors as negative 16 times t plus 2 times t minus 4. Once I have that, I check all three factors. Again, negative 16 equals 0 doesn't make sense. Cross it out. I checked t plus 2 equals 0, but I got t equals negative 2, which again is before they threw the ball, so that doesn't make sense. But t minus 4 equals 0. I added 4 to both sides. I got t equals 4 seconds to reach the ground, and that one did make sense. Okay, so we'll see those types of word problems. The next thing we need to look at, though, is sometimes you're going to be asked to identify the intervals of the function where it is positive. Now, if we think about this, we learned already this year in chapter 1 that graphs are positive when they fall above the x-axis. Oops, sorry about that. So I am looking for anything on the graph that falls above this highlighted yellow line. Now, we could also connect this back to what we learned already, and that is that this is going to be a quadratic, so it's going to be a U-shape. It's going to be open up because A is positive. And if we combine all of that with what we just learned in terms of factoring, the factors will give me the spots where it crosses the x-axis. It gives me the zeros. And if I have those, then I would be able to identify the situations or the intervals for which it's above the line. Now, before we look at this graphically, or we'll probably look at it graphically first, but then I'm going to show you how you can also analyze this in a table. But no matter which method you like, you will have to factor first. So I look at this equation. Again, I'm multiplying to a negative 3, adding to a negative 2. We actually just did this one, 1, negative 3. So my factored form is x plus 1 times x minus 3, which means that it has x-intercepts at x equals negative 1 and x equals 3. So if I was to quickly graph it, negative 1, 1, 2, 3, again, just a general sketch. Oops, sorry, I got a little shaky. It's going to look like this, which means my answer is going to be the intervals where it falls above that x-axis, so those two green parts. Having said that, with what we learned before, we'd say this keeps going to the left forever, so it's positive from negative infinity until it hits this point, which is negative 1. Now, 0 is not considered a positive number, so I'd put a parenthesis. And then I would start again at the next intersection point, intercept point, which is 3, and it keeps going to the right forever, so 3 to infinity. Now, if you understand how to graph a quadratic given this information and you can find those zeros quickly, this is actually a fairly efficient method, but it does combine what we've learned earlier this chapter with graphing quadratics. And in this case, if you use this method, if it said when is it negative, you would just pick the section below. Having said that, I do want to introduce the other option that the book gives to find when things are positive and negative, and that is you would build a table where you virtually write the three intervals that happen. You have one interval where x would be less than the negative 1. You have the middle interval, which is where x is between -1 and 3. And then you have the final interval, which is when x is greater than 3. Okay, so really, we are talking about these 3 different sections that we can see in the graph that we made. If you do this, then you would just use a test point in every section. So I would pick a number less than -1, so let's say -2. I would plug it back into the original problem. -2 squared is 4, plus 4 minus 3. 8 minus 3 is 5. And because I got a positive answer in that interval, this is one of my solutions. So I would say it's positive when x is less than -1. I would test a point in the middle. I always like to test 0 when I can. So 0 falls between -1 and 3. So I do 0 squared minus 2 times 0 minus 3. 0 minus 0 minus 3 is -3. This is negative. So in this case, that would not be part of my answer because it was asking for the positive sections. And then last but not least, I would check any number greater than 3. So I picked 4. So I do 4 squared minus 2 times 4 minus 3. 16 minus 8 minus 3. 8 minus 3, I get 5 again, which is another positive number. And so since I got another positive answer, that would be another section of the graph that's positive. Now again, this is inequality notation. X less than -1 is the same as -infinity to -1. X greater than 3 is the same as 3 to infinity. Again, this is inequality notation. This is interval notation. So just be careful when Pearson asks for it to put it in the right form. And again, you could get that same either form from the graph as well. So those are 2 different strategies to accomplish the same goal. I want you to try this one out on your own. I want you to pause it and just note that this time it's asking when is it negative. When you're done, go ahead and come back and check your work. Okay. So hopefully you remembered that the first step is to factor the x squared minus 4x minus 21, and I got x plus 3 times x minus 7. You can see my work in between. When I set each factor equal to 0 and solved, I got x equals -3, x equals 7. So once again, if I went to the graph, it means that those are the x-intercepts, and because my a is greater than 1, it means it's opening up. If this was a negative, I'd have to make sure I flip it. Now again, because we're talking about, in this case, when it's negative on the graph, it means I would describe this section when it falls below the x-axis. So looking at the graph, I would say it's below the x-axis from -3 to 7, and that would be my answer. If I use the table, I would still use those 3 intervals. X is less than -3, so that describes this portion of the graph. From -3 to 7 is the green section. And then x greater than 7 is that final section. Parabolas will always be, or most often, if it has 2 x-intercepts, I should say, be broken into those 3 sections, the 2 outsides and the middle. Now, I had to pick a value less than -3, so I chose -4, and you can see I got 11, which is positive. But that means that is not an answer since we're looking for the negative. When I picked a number between -3 and 7, again, I chose 0 because that's an easy number to work with. I got -21, so that is a solution. So -3 is less than x is less than 7, which is the same as -3 to 7 in interval notation. And finally, I picked a number x greater than 7. I picked 8, and I got positive 11, which means that is not part of my solution. So again, either method is good, but it's actually really good for you to understand both as well. All right, last but not least, the third concept for today is we want to be able to write an equation of a parabola in factored form if we're given different pieces of information. So in this case, you can see it says write an equation of a parabola with x-intercepts. That's going to be important. In today's lesson, you'd have to be given the x-intercepts, and then it passes through -320. So in these types of problems for this lesson, you'd be given x-intercepts and another point. Okay, because really what we're looking at is we're looking at the form y equals a times x plus something times x plus something else, depending on how many one of these for each x-intercept. And then we'll figure out the rest. Now, having said that, if I know that an x-intercept is at x equals -2, and I want to find the factor, we actually have to work backwards. Remember, when we have a factor, we start with x plus whatever, and we set it equal to 0 and solve, which means we move this to the right. In this case, I would have to move this back to the left to figure out when it's equal to 0. So x plus 2 equals 0. So in order for me to figure out what goes in these parentheses, so y equals a, the first one is going to be an x plus 2. Now, you don't have to show this work that I'm showing, but it's important that you understand how you get there. Again, if I have a -1 as an x-intercept, and I need it as a factor, I go the opposite way. So I move that -1 to the left. I get x plus 1 equals 0. And remember, it's the factors we set equal to 0. So I take the x plus 1, and that's my other factor. So if you're given x-intercepts, the first thing you need to do is write each of them as a factor, like I just did. Now, this other point comes into play next. They're giving me an x and a y value. So I'm going to plug the 20 in for the y. I don't know a yet, and I'm going to plug -3 in for both x's. And now we have an expression that has just one variable, a, and that's what we're going to solve for. Order of operations says to simplify inside parentheses first. -3 plus 2 is -1. -3 plus 1 is -2. -1 times -2 is +2. A times 2, divide both sides by 2. I get a equals 10. Last but not least, don't forget to put it all back together. Y equals, my a now is 10, times those two factors I came up with, x plus 2 times x plus 1. That is an equation of a parabola in factored form, given two x-intercepts and a point. All right, let's finish up by letting you try an example of this on your own. So go ahead and try to write an equation of a parabola in factored form with the x-intercepts 3, 0 and -3, 0. That passes through the point 1, 2. When you think you've got it, unpause the video and check your work. Okay, so hopefully you were able to see that with the first x-intercept, x equals 3, you would subtract 3 and you get x minus 3 equals 0, so that's my first factor. The x equals -3 would be x plus 3 equals 0, so that was my second factor. In step 2, I plugged 2 in for my y and 1 in for both of my a's. Simplified inside parentheses, got -2 times -4, which is -8, divided both sides by -8. And in this case, you did end up with an a equal to -1/4. If you put -0.25, that's fine as well. So your final equation is y equals -1/4 times x minus 3 times x plus 3. All right, so that's it for today. If you want to read a quick summary of what we've been through in the last couple of days, here it is. Shows a visual of some of the concepts we've talked about. Otherwise, you should move ahead and start working on your 2-3 day 2 Pearson practice.